All right, so welcome back everybody for today's session of the Cardiff analysis seminar. So welcome back after the bank holiday Monday. So I hope everyone had a good time, though it was raining pretty heavily, so that's sad. So today we are delighted to have Armin Schikorra from the University of Pittsburgh, who will talk about scale-invariant tangent point energies for knots and fractional harmonic maps. So thank you very much for accepting our invitation, and the floor is yours.
All right, thank you very much. Thanks for having me. I planned on May to be there in person, but that didn't work out. But I hope we can repeat that at some point, especially in the pub. So whatever I talk about today is joint work, before I forget saying that, with Simon Blatt, Philip Reiter, and Nicole Vorderobermeier. And yes, I want to talk about knot energies. And well, the story somehow, if I understand correctly, that in the 1980s, there was like a question in topology about how to find, like by the calculus variations, optimal shapes of knots. And so the idea was, how do we cook up a functional? Maybe that's the first step. How do we cook up a functional that measures how nice is a knot, right? Or how do we measure anything about a knot, about how it's nice? And just to give you like a first idea, I will mostly talk about the tangent point energies, but I want to start with the O'Hara energies because they were the first one, and they were the first one we could do something about. Let's start with the O'Hara energy. So what can we measure about this knot, like analytically, that kind of tells you how good it is or how bad it is, right? How good it looks, how bad it looks. And so when we look at this knot, this explicit knot, what do we like about it? Well, we probably like this part. It's very nice, untangled. And we dislike this part, right? Where it's tangled. So what is that analytically? Or how could we describe this? Keep red. So what happens here? If we look at 2 points of this knot, what we could observe, and what O'Hara did observe, is somehow what is nice about this part is that the Euclidean distance, or the extrinsic distance between those 2 points, is not too far off from the intrinsic distance between those 2 points, right? So there is a metric distance between those 2 points, intrinsic to the knot, and there's a Euclidean distance, the extrinsic embedded distance. And well, they're not the same, it's not a straight line, but they are not too far off. Clearly the Euclidean one is the shortest one, but these are somewhat comparable. And at points where you have like this kind of knottedness, if you want, you would say maybe it's not so nice. I would do this one because it's simpler to draw. So if you look at 2 points here, what you see is that the Euclidean distance, so the extrinsic distance, gets very short, and the intrinsic distance, which I will try to draw now, it goes up here, gets relatively large. So somehow you could get the feeling that somehow measuring like intrinsic versus extrinsic distance, so the length of the red line to the green line everywhere, in some average sense, could give you something about how unknotted the knot is, right? It doesn't care about the topology, it just cares about how, how kind of crumbled, how tangled it is. All right, if we accept that as like some description of something, right? You have to start somewhere. No, wrong direction. Then you can cook up an energy. Right, and when you have an energy, you can try to minimize it. So that's the plan. So let's take a knot. So a knot is simply a closed curve in 3-dimensional space. So let's say a map from S1 into R3, or homeomorphism, 1-to-1, injective, everything smooth, right? For starters, no regularity issues. So maybe a diffeomorphism of the sphere, an embedding of the sphere into 3-dimensional space. It's very easy if we have a parameterization to measure the Euclidean distance between 2 points, gamma x and gamma y, absolute value, that's easy. The knot intrinsic, the metric distance between 2 points, is a bit more annoying, but it's also easy analytically, right? It's just this integral over gamma prime of t from some point t0 to t1, wherever these points are. Okay, actually there's a minimum between 2, right? We kind of take this and then we take the other one, the other distance, and we take the shortest one. But it's an easy formula to write down, just lengthy. how we measure the intrinsic distance between two knot points, right? So these are analytically easy to write down. Now we take two exponents, alpha and p, and we just compute kind of the difference or the ratio between the Euclidean distance and the intrinsic distance at every point, and we integrate over this. Now, I mean, you could argue, why don't I use the ratio? Well, the way it's written now is if the Euclidean distance gets small, this first term tries to go to infinity, and either the intrinsic distance also goes to 0, and then these two compensate because there's a minus sign, and hopefully something stays finite, right? If they're comparable in length, they stay finite, and this is a finite value. But if only the Euclidean distance goes to 0, but the intrinsic distance doesn't, like at this point here, right? If we're in this point, somehow this becomes small, this doesn't compensate, so this whole expression becomes very large. All right, so we have this difference, and kind of this is allowed to compensate for this. Clearly, this is positive because Euclidean distance is the smallest, right? It's always the smallest distance. So that's a positive number. We can take some power. For technical reason, I do p over 2. This is just that p equals 2 is the Hilbert space case. And then, well, of course, I want to have it parameterization invariant, right? So if I change, if I have the same knot, but it's just a different parameterization, it goes a bit quicker here and then a bit slower. I don't want things to change. So here I have the Jacobian, which in one dimension is just gamma prime, right? So these guys here just make it in parameterization invariant. A different parameterization of the same picture gives me the same energy. That's all. All right, and now I have an energy, cooked up an energy, not me, right? So Hara did that. We have cooked up an energy with certain exponents. And it somehow could measure, this is very heuristical argument, it could measure how kind of far away on average every strand of this knot is, right? Kind of measures the distance of different strands. Okay. All right, and now you can start to minimize, and the first thing you can do when you start to minimize is rescale things, right? Why not just rescale this whole thing and see what happens? And when you rescale, you actually see, unless alpha times p equals 4, just making the knot exactly the same shape, but like take 4 times the knot, okay, that would be larger, or 1/4 of the knot, changes the energy, right? If alpha times p is not 4, that's a computation to do, you get that rescaling, so just zooming in or zooming out in the picture changes the energy of the knot. So we don't want that, so we restrict to the scaling invariant case, right? So we will restrict to alpha times p equals 4, so that it doesn't matter when you have a shape of the knot, whether you look from it from very far or very close, it doesn't change anything with respect to the energy. So now we have an energy that, you know, arguably describes somehow the shape of the knot or something about the shape of the knot. It doesn't like self-intersection, right? Because then this becomes large and this doesn't. So they're kind of is self-repulsive in some sort, some form. And it doesn't matter what my parameterization is. That's kind of an internal variable that doesn't matter for the energy. And it, again, the zooming doesn't matter. And of course, moving around translations also don't matter. They don't change anything. All right, so this was done by Juno Hara, as I said, in the early 90s, as a proposal for like an energy which we could use to then minimize, maybe in some knot class, it would be isotopy class in this case, but you minimize this in some knot class, and hopefully you get the nicest representative of a knot. And as I said before, it's translation invariant. Moving around doesn't change anything. Reparametrization doesn't change anything. It shouldn't, right? And now it's also scaling invariant in the sense that if you kind of multiply the knot by a number, it doesn't change. Right? You zoom in, zoom out, it doesn't change anything of the energy. And now you have an energy, and now the questions that you always ask in calculus variations are, okay, given a knot class, so again, this is an isotopy class. So two knots are in the same knot class, if you can transform them to each other without self-intersections. Right, so you have the circle, the unknot class, and then you have all the other knot classes like the Bretzel, the trefoil, and stuff. So given a knot class, maybe, can we find a minimizer? Or what is the global minimizer? I'm surprised it's the sphere, right? And if we talk about minimizers, as usual in calculus variations, you kind of expect that you maybe can get a minimizer in some Sobolev sense, right? Some Sobolev minimizer, and then you would like to say, well, that's actually classical minimizer, and it's smooth or something, right? So regularity theory, and I mostly will concentrate on regularity theory because that's the only thing we can do. All right, so to attack these questions, you can investigate geometric properties. So again, this is the energy. I will now restrict to this alpha times p equals 4 case most of the time. And so you have something which you like, which I mentioned before, which is kind of the self-repulsiveness. So this is, we don't like self-intersections. You can classify that in the sense that if you have a curve which is not a homeomorphism, so it has a self-intersection, then the energy will be necessarily infinity. All right. So if you think about, you have these knot classes, so you can move around without self-intersection. Well, the energy kind of respects those in the sense that if you want to do brute force and do a self-intersection to leave your knot class, you have to go through plus infinity. Right? So you kind of are, it's expensive to go from one knot class to the other. So you would hope if I'm in a knot class, I don't leave my knot class because it's very expensive and minimized, right? Following the gradient flow or whatever. However, that is a strong energy wall. And this energy wall has a hole. And the hole are kind of bubbling effects, which you kind of expect because it's scaling invariant. And so the picture, and this is why I like to talk about knots because they are so nice pictures. So this is a bubbling effect. Think about the first derivative. Right? It starts to oscillate very quickly if you pull tight a knot. And the knot has no thickness in this model, right? So you can pull tight the knot arbitrarily small, and in the limit, you lost some topology here, right? This topology is gone at the limit. However, you can imagine, because you kind of have a scaling invariance, if you do that right, that's a proof one has to do, but if you do that right, hopefully you can believe me, that this may not change the energy because it's kind of a scaling if you do this right. The intrinsic and extrinsic distance ratio doesn't really change here if I do this in the right way. So you have a hole, you can leave your knot class in minimizing sequence, for example, by pulling tight, which is a bubbling effect, right? So if you minimize in a given knot class, in a given isotropy class, in general, the minimizer will be in a class below that, right? There's no reason you don't have to stay in your knot class. You kind of can remove topology. All right, and again, this kind of has something to do with scaling invariance. It's kind of expected. All right, and this of course makes it interesting. And so what was shown in the 90s, let's say, were special situations when alpha equals 2 and p equals 2, where this thing is called the Moebius energy. And the big paper in this area is this Friedman-He-Wang paper. And they showed two things. I mean, they showed many, many things, but two things I want to mention here. One is you do have minimizers in so-called prime knot classes. Prime knot classes in layman's term, i.e. my terms, it's like a knot with only one knot component, right? So this here is not a prime knot. This is a composite knot because it has two knotted components, this one and this one. All right, in a bit more specific or correct terms, a knot has a product operation, which is gluing. You can glue one knot to another in a reasonable way. This is a product. And so you're a prime knot, like with prime number, if you can represent your knot as a product, whenever you represent your knot as a product of two other knots, one of the two other knots is the unknot, so the circle, right? So the circle, this corresponds to a 1, right? And then you are prime knot if whenever you represent the knot as a product of two, one of the product elements is a 1. So like prime numbers, you have prime knots. All right. Again, the point is prime knots essentially has one knotted topology and not two, somehow in my simplified mind. All right. So they show that if you're in prime knot classes, you do get minimizers, and those minimizers are pretty regular. The first derivative is still Lipschitz, C11, once you have this, because you're in like the Hilbert space case, you can bootstrap to smoothness and you can actually get analyticity. And if you're not in a prime knot, this is called the composite knot class, like this picture here, then there is some numerics and some intuition that maybe you do not have minimizers, right? So somehow minimizers disappear. Or you minimize and you do not find minimizers. And all of this is very similar to what you have like in harmonic maps. You have like generating homotopy classes where you have minimizers, and then you have composite kind of homotopy classes where you actually have counterexamples for harmonic maps where you do not have minimizers. So the minimum energy is not attained. Okay. So why is this restriction to alpha equals 2 and p equals 2? So this is Friedman, like a topologist geometer who wants the Fields Prize, right? So the point is that this is a very geometric argument. It's beautiful, and I don't really understand it. But here's a picture that I stole from somebody. So if you are alpha equals 2 and p equals 2, and I guess that is the kind of the main motivation that they started to work is that they observe, then you have another additional invariance. And the invariance is Moebius invariance. So if you take your three-dimensional space, you do a Moebius transform, so the interesting one would be the inversion at the sphere somewhere, then you don't change the energy unless you go through infinity, then you change the energy by 4 pi. So you essentially know exactly what happens under a Moebius transform of the image, not the domain, right, the image. So if in the R3, the three-dimensional space, you do a Moebius transform, the energy doesn't change. And for example, for the existence theory, and this is where I have pictures, for the existence theory, you can use that to make sure that you have minimizers in the following sense. You take a minimizing sequence. Now, it could happen that there's a pull tide. There's no reason that there's not, because it's the scaling invariant. You kind of expect there could be a pull tide. But if there's a pull tide like this, what you can do is you can make an inversion at the sphere to kind of make this part very large and the remaining part very small. So you kind of blow up, it's not the right term, but you make big kind of the place where there's a pull tide. You can do that with a Moebius transform, right? You can make very tiny things very big and very big things very tiny. So if you do that around a pull tide, you can make sure that this pull tide never happens. Now you change your minimizing sequence, but the minimizing sequence didn't change its energy, so that new minimizing sequence hopefully converges. That's what they showed. They essentially showed that you can kind of control one topological part. So they have like a notion of topology in a small set, and they kind of make sure that they can preserve in one area of the image, they can preserve the topology. And then you find your limit. In the limit, you had a minimizing sequence, it converges now, and you're done. Works perfectly if you have only one pull tide, right? Then you can work with that pull tide, you make that pull tide bigger, and you make sure that this pull tide doesn't actually pull tight without changing the energy. If you now have a knot which has two pull tides at the same time, you may make it worse, right? You kind of control one pull tide, make it bigger, you make the other one even more pulled tight, right? So this procedure, like geometrically, seems to work only very well if you are in only one knot component, meaning you are in a prime knot, right? If not, you can control one pull tide at the time, and so prime knots this works. This Moebius invariance, this geometric property, only is true, you can show this at least by numerics. I mean, but it's very good numerics. The numbers are so far apart that you probably could prove it if you took the time. Moebius invariance is equivalent to being alpha equals 2 and p equals 2. The stadium curve essentially is one that you can show after a Moebius transform, no way that this is still having the same energy. So Moebius invariance is only true for alpha equals p2 and p equals 2. So this argument kind of doesn't exist anymore once you don't have Moebius invariance. And I don't have pictures for this, but also for like the regularity theory, this is a comparison argument with Blatt and like very intelligent choice of Moebius transforms. So also for the regularity theory, you very crucially rely in this argument on the Moebius invariance. All right. Okay. And so kind of our goal was to understand how important is the Moebius invariance, or if one can get rid of it, because there's a whole class of other energies which, you know, are not understood. We don't know anything about their minimizers or critical knots. And so what we can do by now is some sort of regularity, or we can do regularity theory to some extent. Existence theory is something which, you know, still needs a decade or so. But so I'm talking about regularity theory. And so we kind of found like an approach which is very different from what we did before, or what is this geometric argument, but it's very stable. And so now we are trying to kind of milk this for what it can do and see in what situations this still works. So the thing that we kind of found is the following. As I mentioned before, there's some similarities to the theory of harmonic maps, just like from the results. There, like the existence theory in certain generating classes, the regularity theory, well, not so clear, but anyways, the identification with harmonic maps, like in this game, is that you say you move to the derivative. So the idea is throw away the knot. We cannot deal with knots. I don't understand knots. So instead of looking at the knot, we look at its derivative. So that's gamma prime. Now, the good thing is we're in one dimension, so we can fix the arc lengths, right? That's a very good thing in one dimension. Parametrization is much easier than in, say, two dimensions, where you kind of have to struggle to get conformal parametrization. Here, we just choose arc lengths. If we have that, if we choose arc lengths, everything is conformally parametrization invariant, so that's a free choice. Then the derivative is a map between two spheres, right? Now, the idea is that instead of working with the knot, we work with its derivative, which is a map between two spheres. And what we found is that we can rewrite the original energy, changes a little bit, but we make it so that when you have a critical knot, so knot with its variation, right, a minimizing knot, let's say, for the original energy, its derivative is a critical knot, critical map, let's say, for a new energy. I will show you the energy in a bit. But the variations that we allow are different. So that's the main point. Here, we allow all the variations that keep this a knot. Here, we allow all variations of U that keep it a map from S1 to S2. Right? So there are like somehow a little bit of change in the variations that are allowed. Nevertheless, we can cook this energy up such that whenever we have a critical knot for the O'Hara energy, its derivative is critical with respect to the variations as a map between two manifolds for the new energy. And now we have got a we threw away the knot. And now we have essentially a harmonic map, or geodesic, if you want, type situation. We have a map between two manifolds, minimized or critical. That's, you know, technically not a big difference, with respect to an energy. And those things always have the same Euler-Lagrange equation, at least formally, right? One has to show this Euler-Lagrange equation makes sense, but the Euler-Lagrange equation is always like a Lagrange multiplier type situation, side condition and energy. So the Euler-Lagrange equation is always the variation, the usual Euclidean variation, is zero in the sense of the target manifold, so it's orthogonal to the tangent plane of the target manifold, right? So this is kind of, this is a formally that's always true. Whether this is really true in fact is another discussion, but formally, whenever you have such an energy, you always have this kind of Euler-Lagrange equation. But now the point is that this here, as we shall see, looks pretty much like, well, like a harmonic map, only with respect to like a norm, which is not the L2 gradient norm, but like a non-local norm. Okay. But essentially, this looks very similar to the harmonic map equation, at least structurally. And so we observe that this energy, I will show you in a bit, it's a bit ugly, but essentially it has like a fractional Sobolev norm. It looks like it. And the idea is we know how these fractional Sobolev norm critical points into manifolds behave. We have the regularity. And so we extend the regularity theory for like fractional geodesics, if you want, to this kind of solution, right? Because these are very analytical harmonic analysis techniques. They don't really care so much about the geometry anymore. And that way we have like a strategy to get regularity theory for like this knot kind of question by working with the derivatives. All right, and just to show you that, I mean, it's not pretty, but it's kind of, it's bookkeeping more or less. So again, this here is the O'Hara energy, and here is the new energy, which looks very annoying, but it has like, okay, a bunch of entries. Now, the main point is, again, we kind of need to make sure that the variations change, right? The calculus variations, we have the directions in which we can take variations. They change when we pass from the knot to its derivative. We want to have a critical map as a map between two manifolds. So we have to take care of that. And so there are a bunch of ones in here which don't really matter. For example, the mean value of u, if u is a derivative of a knot, the mean value is 0. The integral of gamma prime, and this is a circular thing, right? So this is 0. U absolute value is constant or 1, whatever you fixed, right? So this here is just a fancy 1. We have to take care because we take variations, but this is not really a dangerous term, right? Just the variations will not keep that this mean value is 0, and they will not keep that the absolute value is 1. So, okay, we have to take care of this. This is the same thing. So here there are a bunch of 1s. This here is a 1. This here is a 1. So the only thing that's really in there is this guy. And everything else is just to take care of variations. All right, so now this guy is in some f, and the f, well, there's a 1, there's a 1. So this is 1 minus something minus 1. And what is in here is this double integral, which is essentially u of x minus u of y squared. Mean valued version, but it pretty much behaves the same way. So what, here's a 1, there's a 1. So this guy behaves like a, whatever a is, to the power p over 2. It's 1 minus minus 1, right? So the 1 kind of cancels. So this is essentially u of x minus u of y squared to the power p over 2, so to the power p, divided by x minus y to, well, this would be 2 in this case. So it looks like, again, right, this looks pretty much like, it doesn't help, but it helps, you know, for the structural observation, this helps to think of this like this. Essentially, this has a very similar structure to this. Alpha times p over 2 is 2. And this is the power p. Right? So if we just keep the ideas that this looks pretty much like this and look at what we can do for this kind of energies, then we're in a good shape to do regularity theory. And this is pretty much what we did. So we had like the theory for like P, whatever, WSP harmonic maps into spheres. We got regularity, order regularity. So this is kind of the toy model. And essentially what we then did is that we kind of used the techniques that we have here for this kind of energy and just brute force adapted them to what we had, you know, what we actually have in this knot kind of theory. But this way we can use like harmonic map theory, extended, like more non-local, non-linear, whatever, for knots, right? All right, and of course, this I mean, so this theory here was initiated by Francesca Dario and Tristan Riviere some time ago now, and this is an extension of that. And then we kind of, you know, more and more techniques were available, and like a bunch of situations for like these kind of norms is well understood by now. Right. So okay, good. So again, the general strategy that we kind of like, because it worked in this one case, is again the following. We have some sort of knot energy, whatever it is. We want to show for now regularity theory for minimizers critical points, whatever we have. Strategy is throw away the knot parameterization, look at its derivative. Rewrite the energy so that its derivative satisfies an equation. Is kind of critical with respect to an energy, so it satisfies some equation. With a bit of luck, this energy has a structure which we kind of somewhat understand well enough to do regularity theory with. Right, so that's always the approach. And I don't know if that's visible in this quickness, but anyways, our kind of feeling is this is a very stable strategy, right? So we don't really care how this O really looks like. There must be some structural assumption. You could probably write down a theorem with like assumption A to A1 to A20. And for any such energy, some sort of argument like this would work, right? This somehow seems like a stable argument for like a bunch of energies. You probably could do something like this strategy to get something like regularity theory, right? But it's not so clear, and every knot energy has somehow different different problems. So our strategy is now kind of, well, to understand better when this works and how this works. The main goal, of course, is to go to surfaces at some point, because there are these self-repulsive energies proposed for surfaces. Well, you know, nothing is really understood there in the scale-invariant case. And of course, these things appear somehow in modeling, right? So I always like to sell this like the knot energy, some DNA coiling or whatever you want, or for surface, some cell structure. Sometimes you want to have like self-repulsive energies, but we don't really understand them, at least in the scale-invariant cases. Something that I didn't talk about that much, and we cannot really do anything for now, but we kind of move slowly forward, is kind of the existence theory, right? And we try to attack this by Sachs-Uhlenbeck theory, which is well understood for harmonic maps. We kind of can extend this to fractional harmonic maps. And now the question is, can we extend it to the knot situation? Again, it seems that the techniques that we have from Friedman here one kind of, you know, stop working in our situation. But what I want to talk about the remaining time is kind of the move to other knot energies, right? It's never that obvious, although in the beginning I thought it would be. And what we can do now is like another type of energy, which I also would like to illustrate, the tangent point energies. So it's another energy also proposed maybe in the early 2000s. So again, you have like a knot, and it's a little bit easier for numerical purposes, it seems, and then maybe also structurally in general. It doesn't have this third integral about the lengths, right? It's kind of more extrinsic, intrinsic, I don't know, type energy. So it goes like this. So let's take a homeomorphism. So like, again, this knot, right? So somehow an embedding of a sphere, maybe topologically a bit interesting, so a knot. All right, then you have this expression, which is pretty meaningless. So what is this expression? Well, if Q equals, I think, 2 and P equals 4, this expression is 1 over this R, and this R is the following radius. So you have the red line, which is a part of the knot. And then you go into one point, and you look at all the circles which are tangent going through that point. All the circles which go through that point and are tangent through that point. And now you look at the one that also goes through the other point, Y, right? So up there, this would be gamma of Y, this here would be gamma of X, this point. So you look at all the spheres going through gamma of X, and the one, and there may be more than one, but then you take the minimum, the sphere that also goes through the other guy, not tangent. All right, so, and you look at the radius of the smallest sphere that you have here. And then you can compute, with some geometrical stuff, right? So elementary geometry, essentially come up with this formula. That's the formula for this radius in 3 dimensions, right? The cross product of gamma prime and, well, whatever comes out here. All right. Now, what does this measure? So again, if we have that these 2 points, gamma of X and gamma of Y, become very close to another, this guy, the circle, becomes very large, right? If they are the same, this circle becomes infinitely, sorry, if they are the same, it becomes very small, right? Right? If I have something like this, if this is my curve, I always have that kind of the distance between those 2 points that's one circle that could be tangent. So if we have self-intersection, this R becomes 0. And so this is 1 over R in some form. So this becomes infinite. So this thing blows up, or it becomes larger, it seems, when we have self-intersections. And again, if you have a straight line, then you would expect that the radius becomes infinity. So 1 over infinity becomes 0. So again, it's somehow a Lagrangian, which kind of likes it when you're a straight line, and it kind of dislikes it when you have like a self-intersection. Right? So it's somehow in what it measures, it has some similarities to this O'Hara energy. Okay. So there were like several people introducing sort of these kind of energies, right? From like applied, I would say applied topology or biology. And so Maddox, Buck, and several people introduced them. Then there was some like more analytical treatment by Strzelecki and Fonda more so. And again, you have like the scale invariant case, which for me is now the interesting one, and the non-scaling invariant case. And for the scale invariant case, we almost have nothing. But we have something, and the something is very important, and that's the best we can do in the beginning. So when the energy is finite in the scale invariant case, you can show, and Strzelecki will show, that you have a topological one manifold. So this means what you cannot have is like a self-intersection like this, right? Because this wouldn't be a topological manifold. However, what you still can have, and actually that's a global minimizer, is a straight line, right? Parameterize the way you want, right? You can go there, then you go back, then you go there, and then you go back. That still is 0 because it doesn't care about the parameterization. So the doubly covered straight line, for example, which is certainly not a homeomorphism, is 0. So the energy can be finite. It can even be the global minimizer for things we wouldn't accept as a knot. Right? It's not a homeomorphism. All right, so in particular, since you have this kind of example, you know that you have no control of anything like Sobolev or anything for finite energy curves. That's very different to this O'Hara type energies where you kind of generally get like Sobolev control. You don't get anything here, right? Because this could be like a Lipschitz map, which jumps around in the derivative and still the energy is finite. Right? So that leads to like a whole set of new problems, namely, you need to talk about what even means, what does it mean to be a minimizer? What does it mean to be a critical point? And then you can talk about possibly regularity theory. Right? All right. And so we started to work. So the first thing was we don't want to deal with these doubly straight lines. So what we have to rule out is that if we have a nice diffeomorphism, like a minimizing sequence, which now looks like a sphere because that's the only thing that I can draw. What I don't want to happen is that this here kind of converges to the straight line without going through infinity, right? And so this is the first thing we could do. Essentially what we say, if we have a sequence of diffeomorphism, they do not converge to a straight line. Indeed, they converge to something which is by Lipschitz and a homeomorphism if the energy stays finite. You have lower semicontinuity and you get a Sobolev control. And that's kind of the most important part because without that, we cannot do any of the regularity theory we did before. But the point is we get a singular set, and that's a bit annoying. It's kind of expected in this stage, but it's later annoying because you cannot really remove it. So you get finitely many points where you expect that you have pull tides. And at the outside of those points, you get like a uniform Sobolev control. Inside those points, we don't know what happens, but these are finitely many. So we can still get that we are homeomorphism globally. The lower semi-continuity, kind of these finitely many points have low enough capacity that we can remove them for these purposes, but not for the Sobolev estimate, which is very annoying. We don't get that the limit is globally Sobolev, which I cannot believe it's not, but I cannot show anything here. Anyway, so when we look at minimizing sequence, we know it converges to homeomorphisms. That's doable. That's what we did here. And I mean, that's a big word here, but essentially the way we kind of approached this, or what we were motivated by, was the question, or was the argument by Müller and Sferak, which is for Wilmot surfaces, or like surface with bounded second fundamental form. There you have the statement, if the second fundamental form is small enough, you kind of control the parameterization, the conformal parameterization, and somehow technically this looks a little bit similar, and the arguments are kind of inspired by this. Our situation is a bit different. We don't have a second fundamental form, right? We have less than 2 derivatives, so there's no second fundamental form here. However, we are only in 1 dimension, right? So there's kind of a trade-off. The 1 dimension helps us for the parameterization a lot, but we pay with these derivatives, right? Because we have less than 2 derivatives throughout the under control here. And so the argument, and then once you have it, is relatively easy. What you get is kind of a gap phenomenon. So you get, just point-wise, whenever you are smooth enough, you get that the Sobolev norm is controlled by the tangent point energy on a ball plus tangent point energy squared on the same ball. And now this means that if this energy is small enough, and you already know that these guys are finite, and so they are continuous with respect to the ball, you know that you kind of get rid of this guy. So this is a topological argument. It's a polynomial solution, and the roots are separated. So what you get is, if this energy is small enough, and you know that you're already smooth, then you get the Sobolev norm under control in that ball. And so that's kind of the main ingredient. The rest is a covering, and then you get like a Sobolev estimate everywhere outside a singular set, which are finitely many points. That's kind of a general covering argument. And where you have a Sobolev estimate, you can pass to the limit. And so you know outside, well, where you don't have the Sobolev estimates, these are only finitely many points, and then you kind of work to recover every other thing, like the homeomorphism thing, the lower semicontinuity. It's kind of all getting rid of these singular points. A bit nasty, but then this works. So this is kind of the main ingredient, this gap phenomenon. What is very strange in the local case, if you have a Sobolev norm everywhere outside finitely many points, you have a Sobolev norm everywhere, right? If you have something like this here in every ball outside of a singular set, then you have the Sobolev control everywhere. But that doesn't work in non-local for some reason. For these double integral norms, the covering somewhat doesn't work. Or, you know, maybe I still have to think that I'm just being stupid, but we couldn't kind of get this in the limit globally. Again, this is very confusing for me. Anyways, we get locally uniformly a Sobolev control. And well, this is the same statement, right? So we have some control of the Sobolev norm, and this means that we now can talk about minimizing. So we minimize in some isotopy class, would be the most interesting case. Then you get that the first variation vanishes outside the singular set. That's this whole blah, blah statement. Essentially, it just tells you when you're away from your singular set, you have the first variation is 0. And well, there's some gluing argument, which again, all is a bit nasty in one dimension, in this non-local situation, but one dimension makes life a little bit easier. Essentially, these are like ambient isotopy arguments, which are very similar to the Schoen-Uhlenbeck, right? So this is maybe not that complicated anymore. But again, the point is we cannot really remove the singularities. In the local case, you would always kind of remove afterwards. You have first Euler-Lagrange equations outside of the singular set, and then you kind of remove the singular set because it's just points. But somehow you need the global Sobolev control for that. At least I do. I cannot do anything here. All right, so, but now we know minimizers make some sense. Outside of the finite set, they converge into something which satisfies some equation. So we can do regularity theory and nothing really changes. I mean, the computations are a bit different, but like the strategy is exactly the same. We choose a parameterization, arc length, it's 1D, that's arc length, that's always a good idea. Then we rewrite the energy into a new energy so that critical knot originally induces like a critical map as a map between two manifolds. If we have this new energy, we look at this Euler-Lagrange equation, which always has this structure, and we hope that this looks similar to the Sobolev norm and extend the regularity theory. Right? And so what we can get is whenever we have a minimizer, in the sense of we have a minimizing sequence of diffeomorphisms with respect to the energy, whatever comes out in the limit is C1 alpha, derivative C gamma, right? Outside the singular set. It's extremely annoying to me that we cannot deal with the singular set, which again feels a little bit like that I'm just being stupid here. It's very surprising that this doesn't work. Again, it may be just me. What we also didn't attack yet, because there are several problems, but is the existence, right? So this means this is kind of, okay, you'd have any minimizing sequence converges to something which should be smooth. That's what you would expect. Now what you would like to do is kind of to do this reparameterization that you say, well, a minimizing sequence, I can reparameterize in a way that it converges to a minimizer, at least in the prime knot classes. So this is kind of the next step, and this is something we now want to do. So this is kind of doing Sachs-Uhlenbeck for these kind of energies. That would be the natural next step. And of course, again, as I mentioned before, kind of our goal is that you know, this gets even worse in surfaces, right? So surfaces is a thing that we want to understand. And really in the scaling invariant case, I'm still optimistic that we kind of get these kind of regularity results done. But for now, there's nothing really that is understood. In the scale invariant case, once you're above the scale invariant case, you have embedding theorems and you kind of have more control. All right, I think that's a good time to stop. I spare you the technical details. Maybe I just show you this thing. So again, it gets very nasty technically, but it's mostly bookkeeping, right? Once you kind of have the main strategy mapped out. All right, I stop here, and thank you very much for your attention.
Thank you very much for the excellent talk. So do we have questions?
Yes, maybe I can start with something. If you look at the original knot energy and at a gradient minimizing sequence, you wanted to, so the aim seemed to be that you don't leave the knot class, right? By using a blow up. But what does it do if you just let it go? Will it like pull tight many things to remove topology and then get to the prime knot class?
Yes.
Will it do that? Is that shown?
Well, so you have so the statement for the Moebius energy, where you essentially understand most, is there are minimizing sequence which will leave your knot class, right? They pull tight and probably just become the unknot, at least when you have one knot component. I think that can be said. And with this argument by Friedman and Wang, you can also have a minimizing sequence which doesn't do that, right? So you have one minimizing sequence which kind of pulls tight and moves to the unknot, to the circle, around circle most likely. And you have the other one which stays in its knot class and is like a, you know, pretzel shape or something.
But the circle will have energy 0, right? So they can't both be minimizing sequences.
Well, so they are minimizing within their isotropy class, right? So the circle has energy 4 pi, but you know, you can subtract 4 pi, then it's 0 as it should be. But so you have the minimizing sequence in the knot class where we say we have like a trefoil, right? I cannot draw these things, like a pretzel, right? So you have whatever is the minimizing energy, but in the limit you can fall below that, right? Because you just leave your knot class.
Right.
So the energy of the unknot is smaller than the energy of any pretzel knot.
Right.
Something like this should be true. Right. And so if you either you have kind of strong convergence and you stay in your knot class, or you have only weak convergence and you fall down to the unknot.
Okay, thanks. I have to think some more about that.
Any more questions for the speaker? That doesn't seem to be the case, so let's thank the speaker again for the very nice talk. Thank you very much.